Welcome to this final lecture of the course Computational Hydraulics. This is course summary. I will be covering all the modules in this particular lecture. So, we have covered all total 6 modules starting from introduction to computational hydraulics, numerical methods, groundwater hydraulics, surface water hydraulics, flows in pressurized conduits, and finally to interaction of different types of flow. So, what was the course objective? So, at the end of this course, students will be able to solve basic problems of hydraulics using computational methods. So, at the same time they will understand the discretization used in different standard softwares, and they can use their knowledge to identify the best suited software or standard code for their practical use. So, in module 1 which was introduction to computational hydraulics, we started with this overview unit and we defined our computational hydraulics. So, what is computational hydraulics? Computational hydraulics provides a quantitative description of hydraulic system by means of numerical methods and under budgetary constraints. So, obviously this budgetary constraint means that we have computational limitation or limitation of computational resources. So, objective of this computational hydraulics empowers scientists, engineers to perform numerical experiments in a virtual laboratory before experimenting physically. This unit 1 also we have summarized our different module names, this groundwater movement, surface water flow, flows in open channel, surface flooding, flow over hydraulic structures, pressurized conduits, interaction between surface water and groundwater flows. In unit 2 we have discussed about problem definition and governing equations. What was problem definition? Problem definition is in terms of mathematical conceptualization in terms of our ordinary or partial differential equations, and ordinary or partial differential equations these represent conservation laws, mass, momentum and energy in general or simplified form, an ODE equation with one independent variable, and PD is equation with 2 or more independent variables. In unit 3 we have discussed the classification of problems based on initial and boundary conditions. So, initial and boundary conditions that we have discussed. So, for that one we started with this boundary conditions, Dirichlet or specified boundary, Neumann or flux boundary, Robin or mixed boundary condition. We have restricted ourselves to the Dirichlet and Neumann boundary condition in this particular course. Classification, we have classified initial value problem, our boundary value problem, partial differential equation with boundary value problem, initial boundary value problems. Then in unit 4 we have discussed about classification of differential equations based on physical behavior, equilibrium problem, marching problem, completeness of problem definition, well posed, and this was ill-posed problem, ill-posed problem, ill-posed problem, and next thing we have discussed about the classification of second order PDE, whether it is elliptic, hyperbolic or parabolic, that we have discussed. And at the end of module 1 we have summarized our total course in terms of this particular flow chart, and we started with problem definition, mathematical conceptualization, domain discretization, numerical discretization, algebraic form, solution process, whether it is linear, nonlinear, results, and end up the structure. In module 2 we started with this module unit 1 which was overview about the total numerical methods, description, Eulerian or Lagrangian description. In Lagrangian description and Eulerian description, out of this we have covered only Eulerian description of the problem, and we have solved only this type of problems. Domain discretization have covered finite difference, finite volume and mesh free methods. In finite difference approximation in unit 2 we have seen that for boundary node to get higher order accuracy, we need to incorporate more number of points, but for internal nodes we can get a higher order accuracy with symmetric node distribution, that is I minus 1, I plus 1. And with this approximation we can solve our problems. In unit 3 we have discussed this ordinary differential equation and first order ordinary differential equation specifically, that is initial value problem. And initial value problem we have discussed Euler, modified Euler methods. Also we have covered RK2, RK4 and RK3 also. Unit 4 we have discussed this ordinary differential equation which is boundary value problem, because it is a steady state problem and boundary values are defined at two boundaries. This is the left boundary, this is the right boundary. Left boundary, it is having specified boundary condition, and on the right hand side it is a 0 flux or 0 Neumann condition, because it is a impermeable boundary on the right hand side. Next we have discretized our governing equation, which was general governing equation in terms of finite difference grid, and we have seen how to solve this boundary value problem or a steady state governing equation using different discretization schemes. In unit 6 discuss this initial boundary value problem. Obviously in case of our implicit scheme we have covered n plus 1 level, and these are at nth level because spatial derivatives are discretized at nth level. For our implicit scheme, this was for implicit scheme, this was n plus 1, that all spatial derivatives are discretized at n plus 1 level, and time derivative considers n plus 1 and nth level. We have also discussed this Crank-Nicolson scheme, which considers n plus FOP level, which is the intermediate level, and intermediate level we have used hop step as explicit and hop step as implicit to get the solution. Unit 7, we have discussed this partial differential equation and numerical stability of initial boundary value problem using von Neumann stability analysis, and we have also considered this discretization error, round off error during this stability analysis. And numerical stability of PDEs, we have seen what is this CFL condition or Courant-Friedrich-Lewis condition. So, in this case, if you have one pure advection problem without any loss of information, let us say that one this trapezoidal wave, this is travelling in the downstream direction, let us say this is u x t, and it is travelling in the downstream direction with x, and this is for different time, this is time equals to 0. Obviously, if we increase time and if there is no change in the shape and it moves in the rightward direction, which is at future time level, then we can say that it is a pure advection kind of problem, and there is no diffusion in this case. If there is no change in the peak or no change in the shape, then it is a pure advection thing. Otherwise, there may be diffusion and there may be dispersion case where there would be lowering of this one. Finite volume method, we have considered our general governing equation in that case, and this was the advective term. On the right hand side we have diffusion type of term. These are general force terms, this is sourcing term, and we have considered one general system, and we have tried to discretize or to see what is the basis of this finite volume method. In finite volume method, again we have tried to discretize our boundary value problem in unit 10. Then in unit 11 we have discussed the discretization of the same equation or equation that we have utilized in our finite difference case for initial boundary value problem, and we have discretized it using finite volume method. But in this case near boundary the discretization scheme is somewhat different, because we need to consider our no flow or specified flow conditions differently. Finite volume method, this conservation laws we have discussed. If there is change in the values in the upstream and down up gradient and down gradient directions of the cell P, then what will be the procedure for numerical flux calculation that we have discussed in this methods or in these units, upwind method, then Godunov approach, then high resolution methods. In high resolution methods we have flux limiter and slope limiter scheme, but in this case we have discussed only linear problems, but during application we have considered our nonlinear problems. This is unit number 16 of the module 2. We have discussed this mesh free method, which is a point based method, and we do not require base grid or elements or cell for our problem. We can start the problem with number of points which are randomly or which are scattered within the domain under consideration. In mesh free method we have seen that the polynomial interpolation method is equivalent to our finite difference method if we use ns equals to 3. If we increase the number of points in a particular domain, obviously we need to consider more number of points and will not get that banded structure like finite difference case. In moving least squares we need to solve one minimization problem, but after solving that minimization problem we can get the values of this problem in terms of this weighted or weighting function. So, weighting function is important in case of moving least squares. Then we have discussed about the space time moving least squares. In space time moving least squares we use this x domain, this was the t domain. So, for any space time domain problem we have considered both points in spatial domain and temporal domain. And from unit 20 onwards we used this Scilab for writing small codes which is required for this computational hydraulics course. We have discussed about matrix structure and this Scilab in unit 20. Then in unit number 21 we have discussed about this algebraic equation, Gauss elimination. Gauss elimination we have two steps, one is forward elimination, next one is backward substitution or back substitution. Unit number 22 I have discussed this LU decomposition. First step is decomposition, then backward forward substitution, then backward substitution. Then we have discussed the solution of tridiagonal matrix which is by considering the Thomas algorithm or with the tridiagonal matrix structure. And unit number 24 I have discussed this Jacobi's method. In Jacobi's method iteration, this is one iterative technique, and in iterative technique this is our previous time level value and this is updated value. So, updated value depends on only previous iteration values or previous iteration level values, but there is loss of information because we have already updated some values. So, there is loss of information is in this method, that is why this method is much slower compared to usual Gauss-Seidel method. So, in compact form we can write like this. Obviously, this residual depends on only p minus 1 level values, but if we consider Gauss-Seidel method, whatever value or whatever updated value is available, or the updated values are available for the problem, we can directly utilize that value during calculation. So, in this case the convergence is much faster. So, obviously, in this case residual, this depends on p and p minus 1 both. So, in unit number 26 we have discussed this solution of algebraic equation using Newton-Raphson method, and in this Newton-Raphson method we started with a guess value and we can invert the Jacobian matrix, and finally in iterative with iterative approach we can get the solution starting from the guess value. These are individual functions, individually f1 to fn, this should be 0 as per our consideration, but obviously there will be error and we need to update that value using this expression. Now, in module 3 onwards we have started using Scilab as a tool for writing small source codes for different kinds of problems. So, in unit 1 we have utilized Scilab for writing this code for one dimensional flow. In one dimensional flow we have utilized this Gauss elimination, our tridiagonal matrix structure for solution of the problem. In unit number 2 we have discussed the steady two dimensional flow of groundwater, and we have solved boundary value problem or BVP. In unit number 3 of module 3 we have utilized unsteady flow equations for confined aquifer situation, and we have solved those problems or solved that particular problem using this Gauss-Seidel method, and we have used iterative scheme for this method. Interestingly, for the solution of this two index or a two dimensional problem, we need to convert the problem into single index notation for solution using our standard direct approaches, but in Gauss-Seidel approach we can avoid that and we can get the solution without storing the coefficient matrix. In this case the coefficient matrix is constant matrix. So, that is why we do not need to store that matrix. We can avoid that by utilizing our Gauss-Seidel approach. In compact form this is residual Ij, obviously we are utilizing information from p and p minus 1 level. Unit number 4 I have discussed this unsteady two dimensional flow using finite volume method, and you can see that we have utilized the information that we have got from our finite difference method. We have utilized directly that one here, which is forward difference or backward difference, and we have calculated this unsteady finite volume thing. In unit number 4, this unconfined flow, unsteady unconfined flow we have discussed, and module 4 onwards we have started this water or surface water hydraulics. We started with this gradually varied flow, which is initial value problem, first order ordinary differential equation with initial condition, and these are the information like flow depth, x coordinate, bed slope, friction slope, Froude number, discharge, top width, acceleration due to gravity, hydraulic radius, cross sectional area. In this case we have discussed the formulation using usual our information for the prismatic channels. In unit number 2 we have discussed this gradually varied flow and have utilized the Runge-Kutta methods as implicit and explicit, both the cases we have utilized. So, in previous one we have utilized an explicit one, this one we have utilized implicit one. For implicit one we need this Boucher tableau. In this case this Ki is dependent on this K value which is up to I. In explicit case this Ki should be up to the summation I minus 1, which is again a known one, but in this case it is unknown because we are utilizing I as index here or maximum value. In unit number 3 we have started this solution of steady channel flow, single and series, and we have solved the problem considering the flow as a function of x only. We have considered discharge as constant. So, with single variable we have solved this problem. In steady channel flow we have utilized this q and y as functions, because in that case there will be change in the q values in different channels in the network. Unit 5 considers the steady channel flow and channel network without reverse flow. If we know the flow direction like this, we can directly solve our problem by specifying the flow direction here, and we have also used Scilab for writing codes for this one. In unit number 6 we have discussed the steady channel flow and channel network with reverse flow. In this one we have considered a reverse flow situation. If we do not know the actual flow direction, we can start with a assumed direction, and depending on the final answer we can comment on the direction of flow, and in this case we have utilized 3 configurations to solve these problems, and you can see that we have got answers in terms of negative values. That means the flow direction is just opposite to the assumed flow direction. So, channel network with reverse flow we have solved. Then we have discussed this unsteady 1D channel flow problem. In unsteady 1D channel flow, we have considered inflow and outflow conditions varying or time varying conditions at inflow section, and outflow section we have a specified flow depth, and we have solved that problem, and we have seen the variation of y which is flow depth and discharge at a particular section in a particular channel. In unit number 8 we have discussed this 2D surface flow, and unit number or module number 5 we have started this unit number 1, the steady flow in pipe networks. That means discharge is not varying with time, it is a steady state network. In unsteady state case we have considered piezometric head, and in piezometric head depending on the flow situation in transient system, this is one valve there during operating conditions we can get different head values. This is at valve and this is at midpoint, and this is one unsteady flow in pipe problem. This is one important problem for flows in pressurized conduits. And in the final module which was our interaction of different types of flow, we have considered channel flow, pipe flow, surface flow, and from there recharge, and finally groundwater flow with the effect from surface flooding in terms of recharge there. And in that case and in that particular interaction related case we can combine whatever we have learned in the subject, maybe in applied form is M3, M4, M5. We can combine these 3 modules and we can solve this interaction problem using our usual concepts. So, starting from module 1, module 2 we have discussed the methods or background methods. In module 3, module 4, module 5 we have discussed application of the methods that we have learnt in module 1 and 2, and finally module 6 covers the integration of module 3, module 4 and module 5. Obviously, it considers the basic methods that we have studied in module 1 and module 2. So, this is all about the course computational hydraulics. If you have any query or further questions, we can discuss it. You can contact me for that one. And in this one interaction flow, we have considered all the situations there, and this is groundwater flow, and this is the details, my instructor details. I am Anirban Thar, and you can contact me through this email, or you can call me to this number for further discussion. Thank you.